In this tutorial, we'll analyze a plate using a D-plan element. The plate will be 0.15 meter by 0.15 meter. Since we will be using D-plan, thickness need not be applied. We'll apply displacement of 1 to the power minus 5 meter initially, and we'll multiply using a function to make the displacement up to 1 millimeter. The arrangement of the analysis is as shown in this figure. We will also observe a stress and strain at a point inside the plate, somewhere lying on the mesh point, and we'll plot the stress strain curve using code aster alone without using Excel or any other software. So let's get started. First, let's create a new file and let's go to the geometry module. Let's make a plate with size 0.15 meter and also width of 0.15 meter. That's all we'll need. Let's go to the geometry menu, mesh menu. Let's create a mesh. Let's apply that each side will be 3 units. Let's close it, and when we compute, we'll get the mesh. Let's zoom it and see it. Seems fine. Now let's define a couple of groups. The first will be the support edge. We should select the edge, add it, and then apply it. Similarly, let's make the loading edge. Select the edge. We should add it, then apply it. For observing stress and strain, we also need to make a observation point lying within the mesh. For that, let's select the node, and for this case, let's choose this node. Let's name it observation node. That's all we'll need. Let's save the file. Now we can go to the aster study module. Let's add a stage. First, we need to read the mesh. Then we will assign the finite element method. In this case, let's choose everywhere the mechanic phenomena with modelization of 2D plan. Let's also define a material. Notice that we didn't use GC material. Instead, we'll directly define the linear and plastic property. Let's keep Young modulus of 200 gigapascal and Poisson ratio of 0.3. We also need to define the nonlinear part, which is defined by Icaro line. Let's keep d sigma ipsi as 1 exponential 10 and yield stress at 400 megapascal. We need to assign the material. Now let's define functions. First, the function for load. That is, this function will be multiplied with the load. Let's keep a unit displacement at the unit time. For interpolation, we'll use linear, and on left and right extension, we'll also use the linear method. Now let's define the function for analysis part. Let's start at 0 and stop at 100 with interval of 1 second. Now let's apply the boundary condition by assigning mechanical load. First, let's define the support. For that, we'll enforce degree of freedom in x and y direction. Note that we don't have to restrain the z direction as it is the plan element. Now let's define the loading part. Again, it will be a degree of freedom in y direction. The groups would be loading edge. The values would be 1 exponential minus 5 meters. That's all we'll need for boundary condition. For analysis, we'll use static nonlinear analysis for load. First one will be the support, and the second one will be the load itself multiplied by the load multiplier function. For time stepping, we use list R. Since we will also consider plasticity, we'll have to define comportment. For relation, let's use one mesh linear line. We'll use Newton method for the analysis and use elastic method instead of tangent. For convergence, let's define a residual global maxi of 1 exponential minus 3 with maximum iteration of 200. That's all we need. Now let's calculate fields for stress and strain using CalcChamp. For the stress, we will use SIEF INLO. It will calculate stress at the nodal points. Similarly, for deformation, that is strain, we will use IPSI INLO. INLO means the strain at the nodal point. Let's confirm the result is stat nonlinear. Let's name it reaction. Now let's post the calculation in a table using post relativity. The content of reaction, that is CalcChamp, will be applied. For we'll take the output from the nodal point. Seems it's not appearing here, so we copy the name from the mesh module, go back to aster and paste it here. For nomchamp, we'll use stress operation will be the extraction method. Let's name it stress, and nomchamp will be as defined earlier, it will be SIEF INLO. Be careful. Okay. Similarly, for strain part also we need to define it. Result will be reaction. The group of nodes. Now it appears here, so it's easy to click OK. For nom means name of field or name of parameter. This will be the strain part. Using ipsi-ilno. We forgot to define the operation. It will be the extraction method. For output, let's first save the table that we defined in post reliability with file name table1.txt. Format will be table format, and let's keep a separator of comma. To plot the stress strain curve, we need to define a couple of functions with recu function. Let's define the epyy function first from data of table, and we'll extract in x-axis the instant. I will define why we use this one later, and in y-axis we use epyy. Similarly, we define another function with recu function. This will be the stress function using the data from table. Parameter again will be instant. In y-axis it will be SIYY, or the stress. Now we need to plot the graph using these two functions using impress function command. For format we'll use xmgrace with file extension of EPS. Let's give the file name graph.eps. In core way, we need to define the x-axis and y-axis. In x-axis we will put the strain, and in y-axis we'll put the stress. That's all we'll need. Let's save the file. And let's run it. The output table 1 contains many values. The inst parameter that we had used earlier is part of this table, so we had used that parameter. You see the graph, we can see the elastic and non-elastic part. The x-axis is strain and y-axis is the stress. This concludes this tutorial.